Okay, so theorem 3 summarizes what we've been talking about. So it just says matrix equation is logically equivalent to vector equation. Oh my god. That's equation is logically equivalent to, this augmented matrix. Or in more technical terms, you have the vector equation, which looks like summation xi ai is equal to b. The augmented matrix is A augmented with B, and then the matrix equation is AX is equal to B. Oops, this should be A, not A1, it should be AI. Right there, I changed it. So let me just clarify where the matrix A, the first column is A1, it's a vector. Second column is A2, also a vector, ... all the way up to n columns. So this is the hardest part, but it's just a vector equation. It's what we had here. So this is x1 times the vector a1, and x2 times the vector a2, and then b over here. Okay. Example, if A is the matrix 2, 1, negative 4, minus 2, is AX equals B always consistent? So always meaning any choice of the vector B. So is the matrix equation consistent, always consistent? Okay, because we certainly know that you can talk about an augmented matrix as being consistent or not. So we can also talk about a matrix equation being consistent or not, because they are logically equivalent. Okay, so let's see. Well, let's try some things out. If I use an augmented matrix instead, if I fill in those question marks in a certain way, can I obtain an inconsistent matrix? Well, sure. If I go like 1, 1, then I can do one row reduction step. Row 2 minus plus 2, row 1. Now I'll get 0, 0, 3. All right. So the answer to my question is no.